Something is wrong with our universe. A phantom force is stretching the very fabric of space-time, and whatever it is picking up speed. This is the story of the secret force that will decide the ultimate fate of everything. For most of human history, we looked up at the stars and saw an unchanging, eternal cosmos. Then, about a century ago, we discovered it was all expanding. But the biggest shock was still to come. The expansion isn't slowing down, it's accelerating. A secret force, a kind of anti-gravity woven into space itself, is pushing everything apart. This isn't some minor effect. This dark energy makes up about 70% of our entire universe. We have discovered the dominant force in the cosmos, and we have almost no idea what it is. Section 1. The calm before the storm. Our story begins not with an ending, but with a discovery that completely reshaped our place in the universe. For centuries, even brilliant minds like Albert Einstein believed we lived in a static, predictable cosmos. It was a comfortable thought, an eternal stage for the cosmic play. But in the 1920s, that cozy picture was shattered. Working at the Mount Wilson Observatory in California, an astronomer named Edwin Hubble made a discovery that would define the next century of science. Using the massive 100-inch Hooker telescope, Hubble painstakingly measured distant galaxies. He analyzed their light and noticed something strange. The light was stretched, shifted towards the red end of the spectrum. This red shift was a cosmic Doppler effect, a clear sign that these galaxies weren't sitting still. They were moving away from us. The truly astonishing part, though, was the pattern. The farther away a galaxy was, the faster it was receding. This perfect relationship, now known as Hubble's law, could only mean one thing. The entire universe was expanding. The space between galaxies was stretching, carrying them along for the ride. A good analogy is a loaf of raisin bread rising in an oven. As the dough expands, every raisin moves away from every other raisin. From the perspective of any single raisin, all the others seem to be rushing away, and the ones farthest away move the fastest. We're just sitting on one of those raisins, watching the cosmic dough expand around us. This discovery gave birth to the Big Bang theory, the idea that our universe started in an incredibly hot, dense state and has been expanding and cooling ever since. For the rest of the 20th century, scientists worked within this story, and it led to a simple, powerful question. What happens next? Gravity, the great cosmic contractor, pulls on everything. It should be pulling all those galaxies toward each other. So scientists reasoned the expansion must be slowing down. The universe was like a ball thrown into the air. Gravity had to be putting on the brakes. The only question was whether there was enough mass to eventually stop the expansion and reverse it into a big crunch, or if it would expand forever, slowing but never quite stopping. Astronomers just needed to look deep into space, measure how much the universe was slowing down, and declare a winner. What they found, however, was something nobody was prepared for. Section 2. The shocking twist. By the late 1990s, two independent teams of astronomers were racing to answer that very question. They had an ingenious plan that relied on cosmic lighthouses known as Type Ia supernovae. These aren't just any stellar explosions. They are what astronomers call standard candles. They happen when a white dwarf star pulls too much matter from a companion and explodes at a very specific mass, meaning they all go off with almost exactly the same brightness. This gives astronomers a powerful tool. If you know how bright something really is, you can figure out how far away it is just by measuring how dim it appears. It's like looking at a field of 100-watt light bulbs. The faintest ones are the most distant. By finding these supernovae in faraway galaxies, the teams could measure their distance from their dimness and their speed from their redshift. This would let them map the expansion of the universe over billions of years and see exactly how much it was slowing down. But when the data came in, it made no sense. The most distant supernovae, the ones that exploded billions of years in the past, were dimmer than they should have been. They were farther away than a slowing universe would allow. The astronomers checked their math. They looked for any possible error, like cosmic dust, that could explain it, but the conclusion was inescapable. For the supernovae to be that far away, the expansion of the universe couldn't be slowing down. Sometime in the last few billion years, it had started to speed up. The ball thrown into the air hadn't just slowed down. It had ignited invisible rocket boosters and was now accelerating away, faster and faster. This discovery was so profound, it won the Nobel Prize in Physics in 2011. It broke cosmology. Gravity was losing. This forced the scientists to accept a radical idea. Something else is out there. A repulsive force embedded in the vacuum of space itself. They gave this mystery a name, dark energy, and it wasn't a small rounding error. Calculations showed this force makes up roughly 70% of the universe's total mass and energy. Its equally mysterious cousin, dark matter, which provides the invisible scaffolding for galaxies, makes up another 25%. Everything we've ever known, every star, planet, and person, accounts for just 5% of reality. Section 3. The cosmic consequences. The discovery of an accelerating universe changed everything. The old question of a big crunch was replaced by a much darker set of possibilities. If dark energy is a constant property of space, as the standard model of cosmology suggests, then the future is one of chilling, almost unimaginable isolation. This scenario is known as the Big Freeze, or heat death. Here's how it would unfold. For the next few billion years, our corner of the universe will seem normal. The Milky Way will merge with our neighbor, Andromeda. But beyond our local group of gravitationally bound galaxies, the rest of the universe will accelerate away from us. Like those raisins in the expanding dough, distant galaxies will recede faster and faster. Their light will stretch until it's invisible, disappearing one by one from our sky. The rich tapestry of the cosmos will vanish, leaving our mega-galaxy alone in an empty, black void. Over trillions of years, the fuel for new stars will run out. Old stars will die, leaving a graveyard of black holes and dead stellar remnants. Eventually, even these will decay. The universe will become a vast, cold, dark, and empty place. But what if dark energy isn't constant? What if it grows stronger? This leads to a more violent, though less likely, scenario, the Big Rip. The repulsive force of dark energy would become so strong it would tear galaxies apart, then solar systems, and in the final moments, it would shred the very atoms that make up matter. The science is far from settled. For a time, data from projects like the Dark Energy Spectroscopic Instrument, DESI, seem to hint that dark energy might be evolving or weakening. This led some physicists to speculate that a big crunch might still be in our future, perhaps after the expansion reverses in about 11 billion years. However, as of 2026, more comprehensive results from the Dark Energy Survey (DES) have tightened the constraints, showing the data is largely consistent with the standard model of constant dark energy. At the same time, some recent analysis of supernova data have raised new questions, suggesting the evidence for acceleration itself might not be as ironclad as we thought, proving just how much we still have to learn. Section 4. The Hunt and the Human Quest. The discovery of dark energy launched one of the greatest scientific manhunts in history. We know something is pushing the universe apart, but what is it? Is it the energy of empty space? A new, undiscovered field? Or does it mean Einstein's theory of gravity is incomplete? Answering this is one of the biggest jobs in all of physics. To do it, scientists are building the most advanced maps of the universe ever conceived. In the mountains of Arizona, DESI is in the middle of a monumental survey, with 5,000 robotic fiber optic eyes. It's measuring tens of millions of galaxies to create the largest 3D map of the cosmos to date. By tracking the precise positions of galaxies throughout cosmic history, DESI is testing whether dark energy's strength has changed over 11 billion years. So far, the results have mostly reinforced the standard model, but the hunt for any deviation continues. Meanwhile, gravitational wave observatories like LIGO, Virgo, and Kagra offer another path. By detecting ripples in space-time from colliding black holes and neutron stars, these standard sirens provide a completely independent way to measure cosmic distances and the expansion rate. Scientists hope this will help solve the Hubble tension, a troubling disagreement between different measurement methods that could be a key clue to dark energy's true nature. These incredible experiments are all pieces of the same puzzle. We find ourselves in a unique moment. We live in a time when the galaxies are still visible, when the evidence of the Big Bang and accelerating expansion is still written across the sky. Trillions of years from now, any beings in our cold, lonely galaxy will look out and see nothing. The evidence of the grandest story of all will be lost to them forever. The hunt for dark energy is more than a scientific curiosity. It's a deeply human quest to understand our place in the cosmos, to look into the vast, dark expanse and ask, what is this place and where is it going? We don't have the answers yet, but the fact that we can even ask the question, that we can build these incredible machines to chase the echoes of creation, is perhaps the most wondrous thing of all. If you are fascinated by the grand mysteries of our universe, make sure to subscribe and hit the notification bell. We explore the biggest questions in science every week, and let us know in the comments what cosmic mystery should we tackle next. The universe, it turns out, is not a quiet or static place. It's an evolving, dynamic, and deeply mysterious entity. The discovery of its acceleration has forced us to confront our own ignorance, to realize that 95% of reality is made of things we can't see and don't understand. But that isn't a reason for despair. It's an invitation. It's a challenge. written in the stars for the next generation of explorers, thinkers, and dreamers. The final chapter of the universe may one day be cold and dark, but for now, we live in the brilliant light of the cosmic dawn, with a universe of secrets just waiting to be discovered.